Welcome to Temporal Graph Reading Group today. I will let Julia do the intro today.
Sounds good. Hi, everybody. Today we are very happy to have our very own organizer, Andy Shenyang Huang, to present UTG towards a unified view of snapshot and event-based models for temporal graphs, which has been presented at Learning on Graphs Conference 2024. Andy is a, PhD student, finished PhD student at McGill University in Mila, focusing on temporal graph learning, and he's supervised by Professor Raihani Rabbani and Professor Guillaume Rabousseau. He's interested in representation learning on temporal graphs, anomaly detection, and graph representation learning. And he was also the organization chair for the temporal graph learning workshop at NeurIPS 2022 and 2023. His previous research includes change point detection on temporal graphs, COVID-19 disease modeling with temporal contact graphs, and link prediction in temporal graphs. He also enjoys writing Medium blog posts about temporal graph learning. And with that, I will hand over and look forward to your presentation.
Yep, thank you, Julia. Let me know if you can hear me well, and yeah. And then if you have questions, feel free just unmute yourself for any questions. So yeah, so I will get started. So welcome to my talk today, everyone. So I'll be talking about UTG towards a unified view of snapshot and event-based models for temporal graphs. So this was presented at LOG 2024, and this was a collaboration between Vent AI, Mila, McGill, and University of Montreal. So uh, so the outline of the talk today is I will quickly go over definitions for temporal graph, and then I'll provide some motivations, and we'll go through the methodology, see some experiments, and the conclusion. Um, this is slide that's mandatory for every talk on temporal graphs, but temporal graphs are ubiquitous. So we know that a lot of the networks we see are changing over time. And so this means that both nodes and edges can be added or deleted over time, and the features on these networks can also change over time. So these networks are modeled by temporal graphs. So we see a parliament voting network and a flight network here. So in terms of the representation of temporal graphs, so we know that there's two disjoint categories and two lines of research. So one is a sequence of snapshots, or this is more represented as discrete time dynamic graphs. Or we also have continuous time dynamic graphs, which is a stream of events. So these two are separate categories of temporal graphs. And I will quickly go over the definition, but the idea about this paper is that we want to conduct the first comparison and also look into how can we design temporal graph models that can work for both types of temporal graphs. Yeah. So let's look at the definition. So first, for the continuous time dynamic graph, so as recall, we have a sequence collection of edges. So in this work, to make it more general and concrete, we slightly changed the definition. So basically, standard definition are you have a sequence of edges, so source, destination, and timestamp tuple. So here we also talk about the start and an end time for each edge. So this is more general because this you can use to model basically edges with durations. So normally temporal graph learning, like in TGB, we focus on like spontaneous edges. So edges that shows up only one time and doesn't persist. And in real world, we know that there are relationship networks and so on. So that specifies the edge for a certain duration. So to make it more general here, we have both the start and end time, right? And I think for temporal knowledge graph, you also have duration-based edges that basically are modeled as just repeating edges, but these could be just edges that persist the relation for a long time, like being citizen of a certain country or something like that. So here for continuous time dynamic graph, in this formulation, you have a stream of edges that arrives at different time points, right? Oops, I think the animation didn't work correctly. at different time points. And this is best used for online or streaming setting. To know that in this work, we also look at, how to remap these timestamps. So just to mention here that you take these integer timestamps, could be Unix timestamp or second-wise timestamp and so on. You can then normalize these timestamps without loss of generality into a range of 0, 1. So this will give you a fixed range. So basically you divide it by the by something like the max of the timestamp, and you can normalize things between 0 and 1. So this will come important like later on. Okay, so we also have discrete time dynamic graphs. This is more conceptually simple. So here we want to highlight that discrete time dynamic graph make the assumption that your graph snapshots are sampled at regularly spaced time intervals. So this is very important because you're representing the graph as a sequence of graph snapshots. Actually, the time duration between snapshots are not specified usually, and this is usually implicit, saying like you have weekly snapshot or monthly snapshot. So the assumption is that you have a fixed amount of time between snapshots, and the hope is that the models can learn, okay, so how much changes have happened on the graph in this fixed size interval until the next snapshot. So here you're representing as a sequence of static graphs basically. And what I want to highlight here is that, so this is best for data sets where the data arrives in fixed time intervals. So you have monthly or yearly or daily observations, right? Or this is could be due to your data collection that you can only collect data like once a day, for example. And there is fixed duration between these snapshots. And here, similar to before, the nodes and edges also change over time. And the general assumption is that within a single snapshot, you assume that the edges all arrive at the same time and exist for the same time in this snapshot. So they are kind of forming this standard graph. So what's the motivation for this work? So in the literature, we see that discrete time dynamic graph and continuous time dynamic graph. So here I want to make a distinction. So I would like to refer to discrete time dynamic graph. So methods designed for discrete time dynamic graph methods, I would like to refer them to snapshot-based methods. So I'll try to stick to this terminology for the talk as well. So this is to differentiate the design of the method with that of the input data modality. So in this work, we like to see these two types of temporal graphs as simply different input output types. And your model are then working on top of them, designed specifically to work with these concepts. But as we'll see in this work, that like snapshot-based methods, so once designed for discrete time, you can actually make them work for continuous time and vice versa. So here we'll call the DTDG methods as snapshot-based and continuous time methods as event-based. So this is also a terminology from a prior work survey that was presented in the reading group as well. So so here, these two line of research has been disjoint for a long time. So this is something that I noticed since I started doing like research in this domain. And it's very interesting because both categories of methods are actually highly similar, right? So both of them use RNN for some sort of temporal reasoning. So for TGN, for example, you use RNN, you use a memory module to learn recurrent like embedding and updates on your node state vector over time. So keeping track of some sort of node interaction over time. And for RNNs in snapshot-based methods, you are looking at node embeddings and how that changes over time. And both of them also uses GNN to process graph features. So we know that GNN is the dominant way or the most popular way of modeling graphs. So both of them uses GNN to process basically the spatial topology of the temporal graph. So in the event-based case, you process them as temporal neighborhood, and in the snapshot-based case, you process them as graph snapshots, right? Then you get into the differences in terms of the input and output data format. So you have weekly snapshots versus second-wise kind of stream of edges, and also evaluation. Because these two line of research are largely disjoint, they develop separate evaluation protocols to work with them. So for the snapshot-based models, the much earlier work focus on deployed setting, deployed evaluation, which you do not have any new information arriving at test set. So more similar to standard machine learning, right? Then for the event-based models, you have streaming evaluation like we use in TGB, where you predict for a batch and then you can take the correct input for this batch, then feed it to the model. So this assumes that as you make prediction, new information becomes available to the model, not for training, but for updating its internal representation. And then lastly, we have more recent development on snapshot-based, which is the live update evaluation, which allows you to train on snapshots you see during test. So these are all different ways of doing evaluation. And then we have some example methods here, so I won't go into too much detail. But from the snapshot-based side, you have different combinations of using GNN and RNN together to model temporal dependency and spatial dependency. And also there's the phylogeometric temporal library. And then on the right, I think slight mistake on the slide here. So on the right for the continuous time, we actually don't have PyG temporal. So on the right for the event-based models, we have like TGN, like NAT and DiGFormer, DiGLib. So basically you have different category of methods. So the key question that we want to answer here is that, okay, for someone who wants to deploy these methods in practice, so how do I pick which of these methods should I use, right? So how do we standardize the evaluation, and no longer be forced to pick either from event-based category or snapshot-based category. So that's the main motivation. So can we design TG models that can work for both and compare them? So that's why we propose UTG framework called Unifying Temporal Graph. So what this means is that so we present the first framework that unifies snapshot and event-based methods. So in our framework, both type of methods can work on both type of input and output on CTDG and DTDGs. We also enables any method, so any future method through this modification to be applied to either format. So now you can evaluate your method on both type of formats. We also designed a novel training strategy to improve snapshot-based models, taking inspiration from event-based models. So we'll see some of that performance later on. And also this allows us to have first systematic comparison between snapshot-based and event-based models. So this is very exciting to me because now we are able to understand how do we actually design a temporal graph model when you take away the restrictions and kind of the process on the input and output modality. So how can we design methods that are input agnostic for temporal graph learning? So can we take the best of both worlds? Can we take inspiration from both snapshot-based and event-based model and design better future models that work for both categories? Okay, so briefly on how the framework works. So the UTG framework is largely summarized in the diagram here. So you have CTDGs or DTDGs as input, or potentially somewhere in between. So you could you could take your CTDG and then convert it to some DTDG through some steps that I talk about later on as well. So basically, you have a temporal graph as input in the two different categorization, and then you feed it to your UTG input mapper. So the input mapper, very intuitive. This converts the input for your respective methods into the format that they need. So for example, you cannot directly feed the CTDG into snapshot-based models. You need to convert them first into snapshots, and then for similar for the DTDGs, you need to convert them into events and then feed into the event-based models, right? And then so we'll talk about how to do that in more detail. And then you go through your standard TG model training. So here we do standard training for event-based models in batch training. We do UTG training, which is slight modification, somewhat significant modification on the original training scheme, especially for these older models that are designed for the deployed setting. where they do not allow test time updates. So we make changes to them such that they can now able to adapt to test time updates. And we see how their performance improve in the streaming setting. And then we have the output mapper, which then allows you to take the output of these models and project it or directly output into the task that you want, which can be continuous or discrete. Yeah, so that's the overview of the framework, and feel free to ask any questions if you have any. Okay, so I will keep going for now. So I'll go into the UTG input mapper. So conceptually, here's a very simple chart of what you need to do to make this work. So we know that CTDG, so the event-based methods already work for CTDGs. They can be somewhat easily adapted to DTDG, but with some caveats. So we'll talk about that in a bit. And then we also have snapshot-based methods that do not directly work on CTDG. So you need to do some work like for them to do that. And then they directly work on DTDGs. So we'll talk about how the two question mark will be resolved. So more specifically, for event-based models, you need to assign timestamps for them to work on DTDGs. And for snapshot-based model, you need to discretize them, which people have discussed kind of in the past literature to some extent, but not in a formal and like in a standardized way and a systematic way. So we'll talk about the discretization first. So here we want to convert a given CTDG into snapshots such that our snapshot-based models can work, right? So the high-level intuition is that you want to discretize your graph into fixed size intervals. So this is where the 0-1 range from before comes in handy. So previously we showed that without loss of generality, you can take any CTDG and the timestamp within and remap them into a range between 0 and 1. So that's very intuitive. Once you have a fixed range, like 0 and 1, you can then divide them into different intervals. And I will talk about some important note here. So you want to pick time, you want to be aware of time gaps, which can exist for CTDGs, and you want to pick time granularities without time gaps. So I will go into more detail. But conceptually, on the right, you can see that your events are now converted to snapshots based on their temporal proximity if they fall in the same bean or the same interval, and then they are grouped into these snapshots, right? Okay. So let's do a little bit of math. So first of all, we want to define this concept of discretization partition. So this is more formally defining the discretization option. So basically what we do here is you have a sequence of timestamps. Let's say start from 0 and end at 1 for simplicity. And you break them down into different intervals specified by start and end, right? And then a discretization partition is then defined as a finite collection of non-overlapping intervals. And you can also define the norm of your discretization partition as the max of any of the intervals you see. So if you want to partition the graph into equal size intervals, then it means that all the interval size is equal to the max size. So that's very intuitive. And once you partition the graph into these equal size intervals, then they will start to induce graph snapshots, as we'll show in the next slide. But just one interesting question and potentially interesting future direction, though we didn't have time to investigate too much in the paper, is that we know that in the real world, you sometimes want to model uneven intervals. So why is that the case? So intuitively, having daily snapshots are nice. However, we know that in the real world, we have, well, the kind of purchase history or social interactions, they don't really follow a uniform distribution, right? So you do not just send a single message to your family or friends at the first second of each hour. That's not how it works. You usually get a 15-minute break, send a burst of messages, and then you don't send much until after work. Then you start to send more messages again. So the way we behave is kind of irregular in that sense, right? So So one idea is try to design models that can learn these kind of variable intervals that can capture the burst behavior of these edges, for example. So that's just one idea that we had from the project. Now we're going to kind of continue the formulation. So now we have these equal size intervals, and for each interval we can then count the edges that have a start time. And so basically here, to be more specific, we want to look at edges that have a start time that's smaller than the end time and an end time that's bigger than the start time. So these are the edges that will fall into each of the snapshots. Notice that this also works for kind of duration-based edges, the relationship edges, which persists over a long period of time. So this formulation here will then, so for example, if your edge starts in day 1 and ends on day 7, then this edge will exist in snapshot 1, 2, 3, 4, 5, 6, 7, right? So that's very intuitive. So that's what this definition means, right? And here, yeah, here, just another note, the TGB kind of like data sets, for most of the TGB data sets, we have spontaneous network. That means that the edges all belong to a single partition. They show up one time, and for the duration weights, then they can have like multiple partitions, as I mentioned. And now we can go into some more interesting stuff. So now we define the discretization. Now we can define this concept of discretization level. So now you are taking your continuous time interval and cutting it into these partitions, and you can calculate this constant, which is a discretization level of P, depending on the partition you have. So this is defined by the number of intervals. So you take this as 1 over the number of intervals that you decide to keep. And what's interesting here is that this delta or this discretization level notion is naturally that's something you can like understand from a temporal graph point of view. So for example, so what it means to have a single interval, right? So if you just discretize everything to a single snapshot, so what happens? So this will be delta equal to 1. So this means that you have a fully collapsed graph, or in more general term, you have a static graph now. So that's the static graph that people study, is they always have a delta equals to 1 if they come from like a temporal graph. And then you also can have delta equal to 0. So it means that you have close to infinite number of partitions. So this is then preserving your continuous time graph structure, where you could have events that happens at any time, right? So imagine you have infinite partitions, then this guarantees that each of the edge you have in the data set belongs to its own individual partition. So then you best capture the continuous time behavior. So this is when the delta goes to 0. So I think this is some sort of hyperparameter that you can tune with when you design your method and also do in practice. And I think that's this also like interesting to think about as a metric. And then lastly, now with the previous formulation, I will introduce time gap. So time gap is pretty intuitive. So time gap is when you have decided on a discretization partition, or let's say the number of fixed size interval you have, you could sometimes induce a time gap. So time gap is when one of the snapshots have 0 edges in them. So we know that one of the fundamental assumptions for snapshot-based model is that they operate on a sequence of snapshots, and these snapshots have some edges in each one of them for each of the fixed size intervals. So if you discretize your CTDG into time granularity with time gap, it's not clear how these models will behave, or at least that doesn't fall into their assumption. So for simplicity in this work, we always decide on the time granularity to discretize based on the finest time you can do, so the most interval you can do without introducing a time gap. So yeah, and how to handle time gap correctly for these snapshot-based models is again an interesting open question that we find from this work. Yeah, any questions so far? Feel free to unmute yourself if you want to ask a question. So I will keep going for now. So now we know how to convert CTDGs into snapshots. Let's look at how to convert DTDGs into events. So this seems to be very straightforward, but there's two important things that I want to mention here. So conceptually, all you need to do is take your snapshot ID. So you have G0, G1, and G2. This subscript becomes your timestamp, right? So however, when you are doing event-based models, remember that we usually learn from a fixed batch size, which is like say 200 or something that people have been like using for 3, 4 years now. So this is actually dangerous because if you assign the IDs and then you still do a batch of 200 edges, if your snapshot has more than 200 edges, that means you are kind of cutting open your snapshot into two batches. So what it means is that your model is now using the first half of your snapshot to predict your second half of the snapshot, which is typically not what you want to do because you want to predict the future jointly, right? You want to predict entire snapshots at once. So that's something that's to be aware of. So when you are doing the snapshots for your event-based models, you need to make sure that each snapshot have their own batch, no matter the size of the batch. And if the batch like if the snapshot is too large, so let's say you have 1 million like edges in a single snapshot, you can still do smaller batches. But the key here is you cannot do memory updates on your event-based model like TGN, because then that model will then take the information from the previous observed edges, inject into the model, and then use it to predict the rest. So it kind of have temporal leakage in a sense that you are not supposed to have in the regular case. Okay, so yeah, and the final point on this is that actually in most of the CTDG work in the past literature, people do not check if in every single batch, these timestamps are separated. Like you make sure that, okay, there's no edges. Like, so let's say one timestamp have two edges. People actually don't check if the first edge is in the previous batch and the next edge is in the next batch. So I think that's something that maybe going forward that we should start to do, and to kind of remove these temporal issues. Okay, now on UTG output mapper. So now we have learned how to convert our input. So let's see how do we map our output. The most important thing that we want to know here is that, so for continuous time, for the event-based models, the output is fine. They will just predict the edges. For the for the snapshot-based models, they are outputting entire snapshots and doesn't really specify, okay, what time am I outputting? Because the snapshot-based models tend to not take timestamp as input. So here, what can we do? So what you can do is you can look at the size of the interval that you are predicting for, and you broadcast your signal to the entire interval. So basically, for the entire snapshot that I'm predicting, for all the queries you send within the duration of this snapshot, you predict the same signal. So like if you're predicting for edge U and V for snapshot T+1, then for all the duration within this snapshot, you would predict the same answer for the U and V. That's just by design. Of course, this has limitations. It means that the prediction from snapshot-based models are much more coarse-grained than event-based models because you are broadcasting the same signal. So if you make a mistake, then you keep making the mistake. And also, if there are two edges, like if this edge are tested twice and for one time it doesn't exist in this same interval, then the model are guaranteed to make one mistake, right? Because it just by default, it can only make the same prediction for the same edge across the entire interval. And maybe there are better ways to do this zero order hold. So there's first and second order hold, but for simplicity in this work, I would just consider this way of doing things. Okay, so last point on methodology. I mentioned that we try to improve the older snapshot-based models. So how we do is that we want to adapt it for streaming evaluation. So the way we do it is we improve the training scheme. So for the training, we actually take snapshot t minus 1 as input, right? And then this GNN is then asked to predict for the next snapshot. The key difference from before is that previously all the work are accumulating gradient. So you do forward pass on all the snapshots and then you backprop all at once, kind of a cumulative gradient backprop, right? So here we are actually saying that for each step, you backprop immediately. So for each snapshot, you will do a loss and then you backprop. So one thing that we realized that doing this, so first of all, this has better performance. Second of all, what's very interesting about this is that this is linked to truncated backprop through time in RNN training, right? So if you train in this way, essentially you are kind of helping with vanishing gradient problem, especially for very long sequences that are well known in RNN. However, this truncated backprop also have its problem. That means you have a fixed time window, like you are backpropping up until like t minus 1 or t minus 2, like depending on your training, like your select size. Um, so yeah, so there's some trade-off here, but I think there's also like interesting to investigate, and this would extend to not just snapshot-based models for standard temporal graph, but also for like knowledge graph and so on. So I don't know the literature there, but I think there's some theory that potentially could be saying, okay, what's the best way that we do backprop? All right. So going to experimental evaluation. So here we focus on the streaming setting. So here's just a quick slide to show what the setting we're dealing with. So we allows the model to see the edges it has predicted for in the test time, but it cannot do test time update. So which is different from the other two settings. For the methods that we compare, we have quite a bunch. So we have for snapshot-based methods, we have involved GCN, Roland, HTGN, GCLSTM, and even a GCN that we train with UTG training. And for the event-based methods, we have TGN, Graph Mixer, Digiformer, NET, and EdgeBank. And following the taxonomy of TGNN, so actually this is one of the first time that you can kind of compare both sides of the taxonomy together, right? So we'll see some results. So data sets, we use smaller data sets because some of the continuous time ones can take a long time to run. But yeah, but you can also like extend this to the larger data sets. For the snapshot-based method, like for the DTDG data sets, so we test both type of methods on DTDGs and CTDGs. So we'll look at the DTDG first. So first of all, the first, second, and third place are highlighted in color. So you can see that actually Digiformer and NET, which are two of the most recent methods, performs the best on even DTDGs. So beating the DTDG method. What we want to point out here is that this is because they utilize joint neighborhood features, such as like common neighbors and so on of the node pair that you're predicting for. So they are using more design and more like recent like ideas for link prediction. So that could be one of the reasons. The second thing that I want to point out is that on some data sets, the performance of the discrete ones or like the snapshot-based models are not bad. So for example, this specifically for social evolve. So the second place and third place are snapshot-based models, right? And actually the second place is GCN, which means that actually a lot of the dependency, you just need to learn the t-1 snapshot and predict for the t snapshot. And you don't even need to have time encoding because for GCN, we don't even encode the time, right? We don't even have an RNN component. So I think that's very interesting. So yeah, that's for the DTDGs. For CTDGs, which is for TGBL wiki and TGBL review, here we basically have similar observation to before. However, I want to point out that amongst the continuous time models or the event-based models, actually a lot of them have pretty low performance, like Graph Mixer and TGN. And here, more specifically, like HTGN can beat TGN on Wiki, right? And you also have like GCN that even beats Graph Mixer and so on. So I think there are some interesting like observations here that on especially on repeating or like data sets with less novelty, it seems that the snapshot-based models can learn better, um, can do quite competitively. Though like probably you can improve it further by adding more like common neighbor features and so on. And for the review data set, we see that actually for this one, it's pretty challenging for most of the snapshot-based models. And of course, it's highly like inductive, so the edge bank doesn't really work. I want to point out that actually for EGCN and GCN, they have like okay performance, right? They are getting close to the IG former on this case. So which I think is quite interesting. And Roland here is actually kind of yeah, it's kind of better than IG former, which is like again quite interesting. And for the Reddit data set here, we see that the HTGN is actually third place, right? So yeah. And one last thing I want to highlight, second last thing I want to highlight is that there's a significant gap in computational time for the event-based models and the snapshot-based models. So of course, nothing is as fast as EdgeBank because that just reads the edges once and don't need to even compute anything. But outside of EdgeBank, the snapshot-based models are highly efficient. And you can see that GCN is the most efficient because it doesn't even use an RNN. While the other ones are slightly more expensive, it's still orders of magnitude faster than the best performing models. Like DigiFormer specifically is about 35 times slower or even more slower than GCN and EGCN, right? So there's very promising performance and computational efficiency gain potentially to take the best of both worlds. So if we have more efficient methods for computing these common neighbor statistic, and maybe using them on the snapshot-based models, potentially we can have the best of both worlds. And lastly, just to show the effect of the UTG training versus the original. So basically, you can think about this as truncated backprop through time on temporal graph versus like standard RNN gradient on temporal graph. So the difference here is quite significant. So actually, with the UTG training, these baseline models can all achieve quite significant performance boost. And even for the few data sets that are not that different, the performance are basically very similar. So basically, you always want to use the UTG training for these snapshot-based models, at least in their vanilla form. So for conclusion, we propose UTG, a first unifying framework for snapshot and event-based temporal graph models. And we focus on streaming setting for evaluation. And we design new training scheme and also the input and output mapper to allow conversion of these models for different input and output types. The most interesting insights are, so the dry neighborhood features are very powerful, and also sometimes the snapshot-based models can achieve competitive performance to event-based model while being at least an order of magnitude faster in inference time. So future directions, so for example, like we want to build a fast and scalable temporal graph library that supports both snapshot and event-based models, and also like just trying the joint neighborhood features with the snapshot-based models. And one other direction that could be interesting is basically when you are discretizing, you also induce different graph snapshots. And based on how discretized your graph is, I believe that you can actually induce different levels of graph isomorphism. So you can imagine that with timestamps, maybe the graph are easily differentiable, but as you kind of remove more and more on the time information, the graphs become more and more similar to each other. So these are just a few of the future direction. So I will wrap up my talk here, and thank you for listening.
Thank you for the presentation. And I had one question. When you
Mhm.
were talking about the uneven intervals, I thought this was a very interesting direction. And you had an example, the social interactions, and then this burst behavior that some people have this like bursts where they talk a lot to each other and then they stop talking. I imagine it's really difficult to somewhat discretize because, for example, different people have different burst times, right? So you would have to have some kind of non-synchronized discretization. Did you think about that a bit more? How to do
So
that?
yeah, I think it depends on how you want to tackle it. So you could first tackle it as a way of like, well, how to construct your discretization. So that's one perspective. It's like how to, on data set side, what do I do,
Hmm.
right? So how do I map the timestamps more correctly corresponding to these bursts? Or
Hmm.
alternatively, from the method side, you could, let's say, have a specific module in your method that's designed to capture these burst behavior. So you have a regular kind of regular pattern, your time encoding, which mostly capture the regular pattern. You could have another flexible time encoding that captures signals on these bursts. Um,
Hmm.
so conceptually, one thing you could do as a start of this kind of research is um, to basically have a density kind of curve. So imagine you have a 1D curve and you have timestamp as the x-axis. So kind of
Hmm.
like the edge distribution we have in TGP 2.0, right? So you
Hmm.
have sometimes you have bursts and so on. You can then look at, okay, now we have these wave and shapes. So how do we best model these dense behavior, right? Can we capture it with a certain frequency? Um, right? So maybe that could be a parameter that you can set for the models such that, okay, I will guarantee to capture these behaviors. Like, and you want to check if these things are recurring. So if you can capture that as a recurring behavior, I think it's going to help the model. Like, for example,
Yeah.
there's always reading group on Thursday, so we have a lot of researchers here that, at this time discuss like research like ideas, then will form a clique at this time. So we have a burst of edges here, and that's recurring for each Thursday. So can we capture these behavior more explicitly? So theoretically, TG models can capture it through a learnable time encoding function, but in practice, I don't know how well these models are actually modeling these things. Um, like
Yeah.
how learnable that is through just a link prediction signal, for example.
Yeah, that's quite an interesting direction. So thanks for bringing this up.
Yeah, so maybe this could be a like more powerful recurrency baseline.
Yeah. That's a
Yeah,
good inspiration for sure.
yeah. So I think that there's quite a few interesting things. Once you start to formalize these notions in temporal graph, and I think this work have a lot of like interesting directions to go
Mhm.
next. Yeah. Yeah. So thanks for the question, Julia. Is there any question from the audience, or we can also like wrap up 10 minutes early today? Feel free to type your question in the chat or just unmute yourself if you have. Okay. Um, yeah, so I think we can wrap up then. So thanks for coming to the talk, everyone, and I will see you next.